Section 5.1 is on page 331, talks about mathematical induction, and we only have one theorem to really go through. Principle of mathematical induction to prove that P of n is true for all positive integers where P of n is a propositional function. We complete two steps. Step number one, we verify that P of 1 is true. So if we're talking about positive integers, the first integer is 1. If they say non-negative integers, the first integer is 0. You try to do it for the first integer on the list. So you show that this proposition is true. Then we show that the conditional, so we assume that this is true. You suppose that the statement is true for some k. And what you want to show is that replacing k by k plus 1, this would be true for all positive integers k. And that's pretty much the proof. To give you an idea of how summation works, I want to start with problem number 10 first. 10 says, can you find a formula for such a series by examining the values of this expression for small values of n? I'm going to let P of n represent this series. So if I take P of 1, that's simply plugging 1 in there or taking the first term on the list, however you want to see it. That's 1 over 1 times 1 plus 1, which is 2. So that is 1/2. If I want to go for P of 2, that is plugging 2 in there. That'll give you 1 over 1 times 2 plus the second term, 1 over 2 times 3. And if I work this out, that is really 1 over 2 plus 1 over 6, all over 6. That is 3 plus 1, that's 4 over 6, which is 2 over 3. If I want to find the next term, P of 3, that is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over, if I put a 3 there, that's 3 times 4. That is now I could say 1 over 2 plus 1 over 6 plus 1 over 12. All over 12, that is 6 times 2 times. So that is 2, 6, 7, 8, 9. And that turns out to be 3 over 4. Now if I want to go for P of 4, that is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus, when you plug in 4, 1 over 4 times 5. Now, you'll notice this I already added in the previous step. I could have did that here too. Those two are right there, right? And this is right there. So, I could say this is P of 3 plus P of 4. P of 3 is 3 over 4. That's the sum of those. It's right there. Plus 1 over 20. So the LCD here is 5 plus 1 is 6. That is divided by 2, 3 over 10. So, if I look at how this works, P of 1, if I look at P of 2, if I look at P of 3, and just let me make sure, I'm not happy with that one. Oh, I see. That was 3 over 4. So you multiply, that's 15, that's 16 over 4. Divided by 4, that's a 4. Divided by 4, that's a 5. There we go. Now I'm a bit happier with this. So what do you notice? If this goes on, this is P of 1, this is P of 2, this is P of 3, and this is P of 4. If the list goes on, what do you think P of n is? And that's what you're trying to find. What does this sum equal, well, let's see, p of 1, 1 over 2, p sub of 2, 2 over 3, p sub 3, 3 over 4. It seems whatever this number is, you get that number up there, so it's p sub n, that's n over, and the bottom seems to be, the denominator is always one more than that. So this sum is n over n plus 1. Now we want to prove that. That's in part B. In part B, prove this conjunction 1 over 1 times 2. So let's make it official. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over n into n plus 1 seems to equal n divided by n plus 1. So when we want to start this and make it an official proof, according to the theorem, we're going to have to choose let P of n be the proposition, one over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over n into n plus 1 is going to equal n over n plus 1. Well, what do we do first? First order of business, we go for p sub 1. This is step 1. You don't have to write 1, but 1. Either you take the first term or you plug p equal 1 in there and you show that those are the same. So by plugging n equal 1, you get 1 over 1 times 2, or you just take the first term. The right side, 1 over 1 plus 1, so 1 over 2 equals 1 over 2, it checks. Now comes our assumption. You assume or suppose. Assume that P of k is true. What does that mean? If P of k is true, that means 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over k into k plus 1 equals k over k plus 1. That's the assumption. Now, for P of k plus 1, what that is, it's the first terms just like we did. But you're going to add one more term. Replace k by k plus 1. And that should equal, if you replace k by k plus 1, denominator k plus 1 is k plus 2. So, I want to use my assumption. So, this right here, I assumed that equal this. So, to write this, you have to tell me that you've used the induction hypothesis. Plus 1 over k plus 1 into k plus 2 equal to this. Remember, you can't use both sides of the equation if you're making this a proof. The LCD for this is k plus 1 times k plus 2. So this is missing a k plus 2. So that would be k squared plus 2k plus 1. And we do notice that this is k plus 1 squared over k plus 1 times k plus, that should be it. Well, this cancels one of those, and you're left with k plus 1 over k plus 2, which is exactly what we want. So in that case, what do you say? Therefore, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over n, the original, into n plus 1 must equal n plus 1, n over n plus 1. So you reiterate the actual equation. And you're done. And that's pretty much it. So this problem I wanted to do first to show you that that's really what those p's are. When you add them up, you're adding the next term, then every time you add a term, that's the first terms all the way until you plug that value in. Now, I'm going to go to number 1. It says prove that statement. So in this case, positive integer, you want to start with the first integer. Well, we say let p of n be the proposition that, and we will list this 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus n times, monkey, n times n factorial equals n plus 1 factorial minus 1. Well, we start with p of 1, that's the first integer. Either you take the first or plug n equal 1 in there, but you get 1 times 1 factorial, and if you put a 1 there, that would be n plus 1 factorial, that's 2 factorial minus 1. This is 1, and this is 2 minus 1, which is 1, so it checks. Now, our second step, assume that p of k is true. What that means, assume that 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus k times k plus 1, k into k plus 1 factorial equals, and if I put a k there, that's k plus 1 factorial minus 1. And if I go for, that's my assumption, to show p of k plus 1, that is literally 1 times 1 factorial, 2 times 2 factorial, k into k plus 1 factorial, plus 1 extra term. Replace k by k plus 1, and that will become k plus 1, which is 2 factorial. And that's going to equal, replace k by k plus 1, that's k plus 1, which is k plus 2 factorial minus 1. Well, how does this work? This is my assumption. So whenever I use that, I'm going to say induction hypothesis. That is simply k plus 1 factorial minus 1 plus k plus 1 times k plus 2 factorial. So now, when I look at this, I say, all right, well, let's see, how are we going to do this? We're going to say this is k plus 1 factorial. I'm going to factor that out of this. Okay, no wonder I'm messed up. It's not k plus 1 factorial. It was k factorial. Wow, it wasn't working. I'm like, what's going on? What is wrong with this? So that would be k factorial and k plus 1 into k plus 1 factorial. There we go. Much better. I was worried this is not going to work. So by my assumption, I'm going to replace my assumption by what it equals. That is k plus 2 factor, why did I highlight this? This part doesn't get highlighted. So my highlight is k plus 1, it's right there, factorial minus 1. Plus k plus 1 into k plus 1 factorial. Now, if I look at those two terms again, whenever you use that induction hypothesis, you have to state that I can factor a k plus 1 factorial factorial out of those two and leave the minus 1 out of it. If I take that out, that's a 1 and that's a k plus 1. And that turns out to be k plus 1 factorial times k plus 2 minus 1, which is really what I wanted to show. Oh, actually, I'm sorry, there's one more step. Now this right here, isn't that k plus 2 factorial minus 1? Because if I take k plus 2 factorial, that is k plus 2 times k, you subtract 1, and you can stop at any time and put a factorial there. So therefore, 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial equals n plus 1 factorial minus 1. Alright. If I look at number 8, so let me write this here, negative 7 to the n plus 1 over 4. So let P of n be the statement. Alright, so if I look at for non-negative integers, I'll show P of 0. P of 0 consists of the first term, or put a 0 there for n. 2 times 1 is 1. The right side 1 minus a negative 7 to the 1 divided by 4. 2 equal 1 plus 7, that's 8 over 4, and 2 equal 2. That one checks. Now we make the assumption based on k. We say suppose or assume that P of k is true. Then 2 minus 2 times 7 plus 2 times 7 squared plus 2 into negative 7 to the k must equal 1 minus a negative 7 to the k plus 1 divided by 4. That's my assumption for P of k plus 1. Well, that's exactly what you see. Two times negative 7 to the k. The next term is 2 times negative 7 to the k plus 1. And that should equal 1 minus over 4 and negative 7. Replace k plus 1 by 1, that's k plus 2. Now, you'll notice this is my assumption, and that's what it equals. So 1 minus a negative 7 to the k plus 1 divided by 4 plus 2 into negative 7 to the k plus 1 is going to equal this mess. Well, let's see how this plays. If I get a common denominator, multiply by 4 top and bottom, that would be 1 minus a negative 7 to the k plus 1 plus 8 times negative 7 to the k plus 1 all over 4. Okay, that's good news. That equals 1 minus 1 of those plus 8 of those, that's positive 7 of those. And that is, oh, get the 8. That's 1. Now, one of those, negative one of those, plus 8 of those is a positive 7 of those. And do you notice that this is 7 to the 1 time out. Okay, I'm going to take a minus out of this and make that negative 7 times negative 7 to the k plus 1. All over 4, 1. Now, if I take this times this is to the power of 1, you will simply add the powers. K plus 1 is k plus 2, which is what I believe what. So therefore, 2 minus 2 times 7 plus 2 times 7 squared two into negative 7 to the k must equal 1 minus a negative 7 to the k plus 1 divided by 4, the original definition every time. Now, 10 we did already. I'd like to look at okay, I'll improve this at the end if I have time. I really want to go for 14 first and get that out of the way. So in 14 it says, so this summation equal n minus 1, 2 to the n plus 1 plus 2. Alright, so let P of n denote the proposition, or be the proposition. I'm just looking for the wording. Be the proposition that the series k equal 1 to n of k 2 to the k equals n minus 1 times 2 to the n plus 1 plus 2. So let's see how this works. Since they're talking about every positive integer, we go for p sub 1. That is, I could list few of these terms actually that would be wise to do. This way you could see it better like the previous problems. Well, let's see how this works. So that would be the first term, that is 1 times 2 to the 1, and that should equal, if you put a 1 in there, that's 0 times 2 to the 1 plus 1 plus 2, that is 2, and this is a 0 equal to, it checks. Now, suppose P of k is true. What does that mean? That means if I list few of these terms, k equal 1, that's 1 times 2 to the 1 plus 2 times 2 squared plus 3 times 3, 2 cubed plus 4 times 2 to the 4th, and the list goes on. Well, when we assume this is true, we're assuming that 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed plus k times 2 to the k equals k minus 1 times 2 to the k plus 1 plus 2. Now for p sub k plus 1, 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed plus 4 times 2 to the 4th plus k times 2 to the k plus the next term, k plus 1 times 2 to the k plus 1 should equal Replace k by k plus 1, that becomes a k times 2. Replace k by k plus 1, k plus 1 plus 1. But I made this assumption. So this whole mess, I'm going to get out of it k minus 1, 2 to the k plus 1 plus 2, plus k plus 1 times 2 to the k plus 1. Well, let's see how this works. If I factor 2 to the k plus 1, out of this, I will have k minus 1. And out of this, I will have k plus 1. And there's a plus 2. That turns out to be 2 to the k plus 1. Those cancel out. 2k plus 2. Now, 2 to the 1 times 2 to the k plus 1, that's 2, and you add the powers. K plus 1 is k plus 2. I'm going to put the k up front, plus 2, which is exactly what I want. So what do you say? Therefore, 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed plus n times 2 to the n must equal n minus 1 times 2 to the n plus 1 plus 2. And that's the official. Now here, I do want us to list induction hypothesis every time you do that, so I could follow your work and see what you're doing. I want to look at let P of n be the proposition that one times 2 times 3 plus 2 times 3 times 4 plus 3 times 4 times 5 n into n plus 1 into n plus 2 does equal this mess. Positive integer, so we start at 1. 1, you take the first term, and you want to show that equals, put a 1 there, that's 1, 2, 3, and 4. Divided by 4, so yes, 6 equals 6, it checks. Now assume P of k is true. What does that mean? That means assume that 1 times 2 times 3 plus 2 times 3 times 4 plus 3 times 4 times 5 plus k into k plus 1 into k plus 2 equals k into k plus 1 into k plus 2 into k plus 3 divided by 4. Well, for P of k plus 1, we are going to take 1 times 2 times 3 plus 2 times 3 times 4 plus the kth term, and then the k plus 1. So replace each of those by k plus 1. Must equal over 4. Boost those by 1. And that's what we want to prove. But I made an assumption that this right here equal that, so I'm gonna pick on that assumption. And I'm gonna use k into k plus 1 into k plus 2 into k plus 3 divided by 4. This is the inductional hypothesis. Plus k plus 1 into k plus 2 into k plus 3, and we want to show you you get that. So the way we do that, we look at those and we say, you know what, we could factor a k plus 1, a k plus 2, and a k plus 3 out of those. And you'll notice if you do that, what's left on the left hand side is k over 4, and on the right hand side is a 1. That is k plus 1 times k plus 2 times k plus 3, and here this is over 1. So to really get a common denominator, you multiply by 4 top and bottom, and that will be k plus 4 over 4, which is exactly what we want. Therefore, 1 times 2 times 3 plus 2 times 3 times 4 plus n into n plus 1 into n plus 2 must equal n into n plus 1 into n plus 2 into n plus 3 all over 4. And that's pretty much it for this section. This equals k minus 1, 2 to the k plus 1 plus 2. Now for p of k plus 1, you're going to list those one more time. Oh, that should equal k minus 1 times 2 to the k plus 1 plus 2. Alright, so by my p of k plus 1, that is 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed plus k minus 1 times 2 to the k plus 1 plus 2 equals, oh, now the next term, this is p sub k. Add one more term. Put k equal